Okay, now we can start. So selection sort is essentially you traverse through the array from the left to right, and then you look for the smallest element. Once you found it, you place it to the leftmost side or like the front of the array. So in the first situation, what you're gonna have is you have an unsorted array, and oh wait, so this is your right, right? When you guys are seeing my screen, sorry, seeing
Yeah.
my
Yeah.
okay, so you can imagine you start from here, so the index 0 of the array, and you traverse through this array trying to find the small element. So once you have like a full iteration of this array, right, you will find like some smallest element in the middle, and then you place it to the leftmost part of your array, which is like index 0, and then you go on, but this time you start looking at index 1, and then when you find the second smallest element, you put it on the index 1 position, and it goes on and on. I wish. Wait, I think do we have an example here? Okay, I wish. I'll. If that is unclear, just let me know. I will like write down a toy array so that we can go through it together. But so is selection source sort of clear? The idea.
Yeah.
Okay, what
Yeah.
about Kathleen? Because you haven't watched the thing yet. So
Yeah. I think so.
okay. Yeah. It's kind of bad that I cannot just share screen my iPad and this computer at the same time because I need to go through the slides. But yeah, we'll see more examples later. So insertion sort is kind of different in that in this one it's that you travel through the array, and whenever you go from left to right, for each element, you want to actually check if you can move it to the wait, swap them. Right, yeah, if you can move them to the right. So that means like if you see some element that is larger than their neighbor, then in a sorted array, right, you will want them to be on the right side of their neighbor. So it's essentially performing a series of swapping. I think for this one, I would actually want to share my screen on my iPad, so it'll be more clear. Um, or wait, actually, okay, so let's do this. When we start doing the questions later, I will try to find some GIF images that shows these operations. So I guess that will save us time. But essentially, the idea is that the runtime is theta of n plus k, and k is just the number of elements in the entire array. Sorry, n is just the number of elements in the entire array, and k is the number of inversions. So you'll imagine like the reason why inversion is important in this case that we want to consider is that we are only swapping when there's inversion, right? So inversion by definition is just that when an element that is supposed to be on the right side of some other element is instead on the left. So assume you have an array of only 2 elements where the first element is like 2 and the second element is like 3. If it is actually 3, 2 instead of 2, 3, then that is an example of inversion. And the number of inversions is gonna determine how many swaps you're gonna make. So that is why we're taking it into consideration in the runtime. And the best case, of course, is that there's no inversion. So you just check through each of the elements in the array, and then you realize that there's no swap absolutely needed. So you'll just stop there. And the overall operations you've done is n operations. And that gives you like a best case runtime of theta of n. And then the worst case is that each element is reversed. So that means, so if you're in a reverse order, then you'll imagine that the first element is actually gonna be the largest element, so that you actually have to swap it all the way to the farmost right side of the array, and that is n operations, right? And for the next element, you have to do n minus 1 operations, and so it goes. I think this is the summation of n plus n minus 1 plus n minus 2 all the way to 1. And do you guys remember what this number sums up to? I think I covered it in our lecture for runtime.
N squared.
Yeah. So that, I think, is the reason why the worst case runtime is n squared. And I just want to check with Ryan.
Sorry, what was the question again?
Oh, so we're analyzing like the worst case possible runtime for insertion sort. So if you have a reversed order array, then for the first element, which is going to be the largest element, you actually do n swaps to swap it all the way from the leftmost side of the array to the rightmost side. And then for the second one, you're going to swap it all the way till the to n minus 1 position on the right. So that is like a series of n plus n minus 1 plus n minus 2. And together that sums up to n squared operations.
Oh, yeah, you have the right idea. I think it's like the other way because the first element does no swaps. And then the second element will do one swap. Because you always assume that the left is sorted already.
Yeah.
So then
So
you're building into that. So it'll be like 1 plus 2 plus dot 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 plus n minus 1. But yeah, you have the right idea.
So it also says that there's n squared operation, but I think if you think of the way that I just described, it will actually be more straightforward than thinking of in terms of inversion. Okay, so heap sort is rather different because for heap sort, you first have to put all your elements in a max heap, and then you want to remove the max heap, the max element on the top, and add it to your to the array that you're building, and then you want to reheap you want to heapify the heaps so that the remaining thing you have is still a heap. So I think Kathleen wasn't here last time for the review on heap.
Mm-hmm.
We've never covered heap in this lecture, but I assume you know all the nitty-gritties on bubbling up and bubbling down, right?
Yeah.
Okay, so can anyone tell me, I guess it's written on the slide, but don't look at it. Can anyone tell me how long it takes to reheap a heap once you remove an element from the top?
Log n.
Yes, it is log n. And would you mind explaining why that is the case?
Yeah, so basically at each level it like divides by 2, so you only have to go through log n of in worst case to go from bottom to top.
Yeah, exactly. So it's all about the number of levels, right? And in any heap that is of a binary, so we're talking about binary heaps here. So in any heap that's of a binary structure, it's if you have n elements, and the heap is like bushy. I think that's always the case. Not sure, but a bushy binary heap will always have log n layers, so you could probably assume that. Actually, for merge sort, I'll actually want to walk it through. This is by far my favorite sorting algorithm, and I just want to give you guys some concrete example on this. So, okay, let me project my screen. So did you guys cover merge sort in the discussion, Shafali?
Yes.
Okay. Yeah, my plan was to have you guys actually derive some of the worst case and best case, but then I realized since we have this slide, we could just go through.
For heap sort, why is it n log n, not log n?
Not log n. It's because that okay, so you put everything in a heap, right? And then you're taking out the elements one by one, right? So when you remove the max for the first time, you only have one element that is in the order that you want, right? But you have to do this remove operation in total n times, right?
Oh, I see. Yeah, that makes
And
sense.
for each of the time, you always have to reheap it. And the overall runtime for that reheaping action is log n. So it's n times log n. Yeah.
Okay, makes sense.
Could you guys see my screen?
Yeah.
So the idea of merge sort is that, say you have some arbitrary array like this. What you want to do is that instead of just sorting this as a whole, what you want to do is that you actually want to split it into half and sort of sort on that half. So what I mean by this is you will first split this array in the middle. So now you are given 5, 1, 3, 2 and 8, 6, 5, 4, right? And then you want to split this into even smaller parts. So 5, 1 and 3, 2, 8, 6 and 5, 4. And then once you're here, you still want to split into even smaller parts. So we are basically going to split the entire array until you only have one element in each part left. So in this case, we're talking about, as you can see, this final layer here has one element each, right? And this is where the magic happens. So now why is it called merge sort? Because you're actually doing the sorting only when you're merging these items. So you'll first start from 5 and 1, and then you're gonna remerge them into like one array back again, which is gonna be an array of length 2. But then you're gonna compare like which one is actually the smaller one. So you'll realize that 1 is smaller than 5. So when you pass them back up, it's gonna be 1, 5 instead. And same thing for here. When you pass 3 and 2 back up and try to merge them, you're gonna sort them, so it's 2 and 3. And now once you're at this layer, what do? You have 2 individual arrays of length more than 1, right? So you will start by having a pointer pointing to their head, respectively, which is like index 0. And then you're gonna compare which of the head of these array is actually smaller. You'll realize that 1 is smaller, so you take that out and you put it down here. And then you move this pointer to the new head of the remaining part of this array. And then you're gonna compare which one's larger, and this time, which one's smaller, and you're gonna realize that 2 is smaller. And then you move the pointer, and you're gonna see that 3 is smaller than 5, so you finally have that. So and this is the same part. So you'll first get 6, 8, and then 5, 4, and then you're gonna first compare the heads. So 4 is gonna be first, and then you're gonna compare 5 and 6, 5, and then 6 and 8. And once you're here, you just do the operation again. So you're gonna see that the smaller head is like 1, then 2, 3, 4, 5, 6, 7, 8. So why is this remarkable? Because notice how once we're dividing this into 2 parts, how many layers of calls do we have in total? Anyone can try this one. It's pretty straightforward.
4.
Okay, sorry, let me rephrase this. Assuming we have an array of n inputs.
Oh, n divided by 2.
No, we actually have log
Oh,
n.
and log n. Yes.
Notice that this is essentially like a binary structure, right? Because every time you're you're splitting a subpart into 2 subparts. So this is log n layers. And what is the amount of work done in each layer? Now we can actually take a look. So for these two, so when we're trying to merge together, actually let's start from bottom layer. When we're trying to merge together these 2 elements, how many checks are we making?
2 or
right.
1.
Okay, you can say like you check the head of here and then you check here, but in the case of only 2 elements, you don't have to do the other check, right? But But say in this layer, right, you're actually just doing at most 4 comparisons. Right?
Yeah.
So,
Yeah.
so we're talking about a more general case. And on this
Okay.
part, it is the same. So you'll realize that essentially at each layer you are doing 8 checks. You can verify it on this thing here, but you'll realize that at most you're doing 8 comparisons. Yeah. So this brings, so in the scenario where we have n inputs, all the amount of comparisons we're doing at each layer, if you sum that up, you'll realize that it's actually gonna be n at each layer. And since you have log n layers, this will be n log n. And I think this is a pretty good instance of, okay, I always like to say like merge sort has very good runtime, but a lot of other sort has similar runtime. So it's definitely not the best or like the fastest you can do, but this is an example of what we call divide and conquer algorithms. So once you finish 61B and go to 70, you will see more of these kind of algorithms where you are given a problem of, you're given like a large problem and you are consistently dividing them up into some sub problems. Not necessarily dividing into 2, you could do like, you could split them into 3. But the idea is that by splitting these problems into sub problems, we can actually reduce the runtime. Than just handling the big problem by itself. Yeah, so any questions on merge sort?
I'm confused on what you mean by like the maximum number of comparisons is 8.
Oh, so, okay, let's run through this again. So are you saying at each layer? Why is like,
Yeah.
Okay, so let's look at this layer, the second layer first, right?
Okay.
So what is the size of each of the array you have here? It's 4, right? So each array has a length of 4, right?
Yeah.
So essentially, if you think of, you can abstract this into like n, but we want to look at some concrete numbers right now, right? And you want to see how these two numbers might bound like the total number of work you do. So remember how we start by comparing the head of each array. So the first comparison, right? You're comparing 1 to 4, and then you realize that 1 is smaller, so you place it in front of the new array that you are making. So suppose this is a new array you're making, and then you don't have to look at this again, right? So you move your pointer to the next element, right?
Yeah.
And now you're doing another comparison of 2 and 4, and you realize that this is 2, and then you're doing another comparison, 3. So we've already done 3 comparison at this point, right?
Oh,
and
yeah.
you'll realize that the total number of comparisons that we can make will not exceed the number of inputs we have in total in these 2 arrays. So suppose you have, say, k elements in each array. We'll realize that the maximum number of comparisons you could make at this call is actually 2k. Right? So we're just trying to bound like the amount of work we are doing in each layer. So by the same logic, we realize that, so notice how when you start with a problem of n, you divide them into n over 2 and n over 2, and then n over 4 and n over 4, right? And it goes on and on and on until you have only one element, right? So how many we're interested in how many how much work we're doing at each call, and also so each call is like one node, but also the entire layer, right? So by this observation that we just saw, how many calls are we making in this node? If you have like 2 arrays of size n over 4.
N over 2.
Yeah, exactly, right? So at most you're doing n over 2 works, and this is the same logic here, right? So you'll realize that the total amount of work you're doing on this entire layer will not exceed n.
Oh,
The
I
same
see.
logic here that you're doing n work, right? So we're just trying to bound like the number of work that we're doing. Yeah.
That makes sense.
Yeah, it's very neat, but I assume like all of you guys will take 170.
Yeah.
So there will be more details
Mhm.
on this later. And you guys will see some way cooler algorithms. But yeah. Just to make sure that you guys understood. Okay, so let's go back to the slide. So quick sort is rather different. So for quick sort, there's this idea of pivot. So you first choose an element that you want to use, and then you are gonna group all the elements in this. Sorry, all elements in this array. You are gonna group them into 3 groups. So your pivot in the middle, and then all elements smaller than the pivot goes to the left, and all elements larger than the pivot goes to the right. So let's see. I might also want to just do a demo on my iPad because this could be also fun. Oh, you guys couldn't see my screen right now, right? I don't think it's showing up. Hold up. This is weird. Shafali, how do you think the discussion actually gave you a good cover on quicksort?
Yeah, it was okay. Actually, the homework this week, inside of it, there was a demo for Quicksort where it printed out the output for each step in the like terminal or like in IntelliJ. So that really helped to understand what's on the left side, what's on the right side, and in the middle.
Yeah, at least when I took the course with Professor Hofinger, I always found quick sort and merge sort the most confusing. So that's why I would like to just do some concrete examples here. But okay, so let's use our toy example once again. So what you're gonna do is that you'll first choose a pivot. So this pivot can be any number that you want. But we'll later see how a good pivot can actually reduce the runtime. That's actually question 2 on our worksheet. So let's just say I choose the leftmost. I choose the leftmost element here as 5, right? So essentially, what quicksort is going to do is that it's gonna place 5 as the pivot element, and then all the elements that's smaller than 5 will go on the left side, and all the elements larger than 5 will go on the right side. So you can imagine something like this. And then once you are done with this operation, sorry, did I make a mistake? Oh, okay, let me change this number so it's less confusing. Once you're done with this, for each of the subparts you have here, so part on the left and the part on the right, you want to do like a quick sort recursively on them. So now we're looking at this individually. We pick a pivot. Let's say we pick 3. Then all the elements, say smaller than 3 will go on the left, and all the elements larger than 3 will go on the right. So this goes like recursively. So let's say we pick 7. And then at the end, so once you do this like towards the end, this entire thing will be sorted. But how exactly do they do it? And what I mean is that, okay, so here's the thing that I think it's something that might not be covered in discussion. So they tell you like, okay, you're grouping elements on the left and right? But like, how do you actually implement, or like in the actual run through, like what is the position of the pointer and stuff like that? So that is what I want to talk about as well. And Ryan, are you still there?
Yes.
Please correct me but if I'm wrong, but I think in quicksort they're keeping 2 pointers and they're doing swapping and things like that.
Yeah, I think it's called horror partitioning.
Yeah.
So it's like a faster way to
To
put them in the partitions. Is there's like a left pointer and like a right pointer, and then they like approach each other.
okay, let me see how I should go about writing this. Did you guys cover like this kind of pointer in the lecture or the discussion by any chance?
I don't think so.
Well, I think you can assume
Oh,
that.
sorry, wait. I think my connection went up. Like Shafali, did you guys talk about how the pointers actually work and like how this thing is ran through?
No, not really.
Okay, so
I think you can just assume the partitioning like scheme is just the usual like you can just put elements like in order instead of doing like horror partitioning.
oh, so it's you're saying that there could be other implementation that's like equally valid?
Yeah, the reason why we do horror partitioning is because if the element has a lot of duplicates, it would be faster. Though I don't know if they actually cover that in lecture. I don't think they'll be tested on it either, but I can keep looking to make sure.
Okay, no worries. Then I guess in that case, let's just put this later and actually start on the problems because there are some pretty interesting problem in this worksheet, and I want to just go through them. And I'll use my iPad. Okay. So sorry for switching back and forth. I just found iPad more convenient than. Okay, so could you guys all see the screen?
Yes.
All right, great. So, okay, I don't want to test your guys' memory, so, but can you guys give me like the best and worst case input of for insertion sort?
N and N squared.
N and N squared. Okay, and do you remember why that will be the case?
So like you have to loop through the whole array and compare it.
And then swap, right?
Yeah.
Yeah, and remember how we talked about in a reverse order list for the largest element, which is like the first element, you need to swap it all the way to the right.
Mm-hmm.
And then for the second largest, you have to swap it all the way to the right, like the second rightmost position. So that's like that series. Yeah, just a recap. Okay, so for selection sort and insertion sort, which one do you think will actually run more quickly on a reverse list? So reverse list is like a list in descending order. This is a tricky question, I think, but you can give it a shot. Do you guys have any idea on this one?
Would it be insertion sort?
And why do you think that might be the case?
I don't know, because I know when the array is smaller for insertion sort, it is more like an n runtime instead of n squared.
Okay, yeah. But for this question, let's approach it just in terms of runtime. So, like analytically. So, you guys might have remember the best case and worst case of a selection sort is all n squared. And we just talked about how the insertion sort is also n squared, right? So what is like the absolutely most terrible thing that can happen to a selection sort? remember how selection sort is finding the smallest element and place it to the left side of the array, right?
Mm-hmm.
So if you have an array like this, what the selection sort is gonna do is it's gonna traverse all the it's gonna traverse this it's gonna traverse this n element, and it's gonna put the smallest element, in this case 1, right, to the left. So notice, regardless of how the order changes, you still need to for each iteration of this finding smallest element action, you still need to take like n checks, right? Because until you go to the end of this array, you wouldn't know like what is actually the smallest element, right? So suppose you encounter some very small number on your way towards the end, you wouldn't be sure that it is smallest until you've seen all the elements in this array, right? So notice that the order of your array actually wouldn't matter that much in selection sort, because you still need to do n checks and to find the smallest element, and you have to find the smallest element n times. So that is sort of why like you can think of it as like they have the same runtime, right?
Mm-hmm.
And then we've also talked about how it is also n squared for insertion sort on this reverse list. But let's dive deeper and actually compare like what might be different in terms of like the actual number of operations. So notice that for selection sort and insertion sort is both like asymptotically they're both n squared, right? So that means asymptotically there will be no difference when they're given a reverse list. But actually selection sort might just do a few less operations than insertion sort. And why is that the case? So imagine you have some reverse list, right? What selection sort do is that it goes to the end and swap this element. So put it in the front, right? I think they actually swap it. And then it does the thing again, find the second most smallest element, and then swap it. So notice that just remember how just checking each of the elements will already take n squared time. Sorry, yeah, that is what we established, right? But notice that for each of the finding smallest element action, we're only doing one swap. Whereas in a insertion sort, we're also just going all the way to the rightmost side, right? But then when we see this 1, we're gonna swap it with 2. And then we're again going to swap it with 3. And until we reach the front of the array. So this single action insertion sort is actually doing way more swap than selection sort. Do you guys see that?
So the insertion sort is basically doing more swapping.
Yeah, although asymptotically they are the same, but there's just like more swapping operation being done. Yeah.
Okay.
So that's how you can maybe think about it. Yeah. So question 1.3. In heap sort, do we use min heap or max heap, and why? This is also a very conceptual question. Not sure if you guys have covered it. But do you guys want to take a guess? Remember what the
we would want a max heap.
And why do you think that's the case?
So if we wait, actually,
you
so
can. Yeah. Sorry.
Well, you have an array, and your heap, and you want to pop off the first element of the heap and put it in the front of the array.
You're saying if you're creating a new array, right?
Yeah.
And then you can you do a mean heap, you can just pop each in order and just place it.
Yeah.
Okay, that is a very, very valid thinking, but there's a slight tweak in this, because do you guys remember the array representation of a heap? Do you
Yeah.
guys, like, remember that? So suppose we have a heap like this. Oh, actually, I think they have it on the slide. So I'll just use the example on the slide. So suppose you have a heap like this. Sorry, 1 second. What max heap allows us to do is that when we remove the element, so the max element, which in this case it's always gonna be, oh sorry, this is the dummy element. This is like the index 0, which is like a null. We can remember how we removed the top of the heap, right? And in the case of max heap, it's actually gonna be a maximum value. And we can simply, okay, let me think of how we can go about doing this. So the good thing is that you can actually just stick okay, so when you remove it, right, in the case of a mean heap, you said that we can create like a new array and just place it in front. But in the max heap, what we can do is that we can, when we remove an element, so that means okay, remember how when we remove the top element in a heap, we want to take the bottommost rightmost element and replace it on the top, right? And then you want to do bubbling down and bubbling up, so to make sure that it is a heap again. So sorry, let me just draw this out. So in this case, when you remove 12, you're also replacing the element -1 on the top, and then you're gonna do what's called bubbling down, so that it's a heap again, right? But so what does it mean? This means that you're actually, notice that you're swapping it with the rightmost element in this heap, right? And then once you finish bubbling down, you're gonna again take the max and swap it with the bottom level leftmost. So notice how in this process, you're constantly sticking the max. Sorry, this is not -1 because I haven't reheapified this heap yet. But you're always taking the max element and sticking it to the back of the array. And once you finish this process, you will have a sorted array from the min value to the max value. And you don't even have to create like a new array. So
Okay,
that
that
is,
makes sense.
so that saves like even more work. And so you can sort of think of max heap as having this great property that once you finish it, the array that you use to represent the max heap is itself like a sorted array. Yeah.
Okay.
And I think it's always the case that we'll use an array as an internal structure for representing heap in this class. So at least I guess in scope of 61B, this will always be the case. Yeah.
Oh, okay.
Okay, so now let's, sorry for taking quite a long time explaining this, because before I drew it out, I don't think it's very intuitive. Okay, so now you want to sort the following array using heap sort. So
Prince, I gotta go.
oh, no worries. I think, yeah. Do you want the recording of this, of the remaining part?
Oh, that would be great. Could you also send me the
already
slides?
1 o'clock. Yes, I will.
Okay.
Actually, feel free to go if you want, but I'll just finish like question 1.
Thank you. Bye-bye.
Bye. Okay, so Shefali, are you staying?
Yeah, I'll stay for question 1.
Okay, so I think heap sort will be pretty straightforward. Do you want to do 1.5 instead? So a quick sort algorithm?
Sure.
Okay,
Yeah.
so let's see. Yeah, so you want to first so let's pick so we pick the middle element as the pivot. Okay, so the middle element here is 1, 2, 3, 4, 5, 6, 7. So notice that there's no middle element, so we pick the element to the right of the middle. So we'll pick 6. So 6 is going to be the pivot. And we have these groups. And then we just do it recursively. So here the element to the right of the middle is 8. So we'll have 8. And then 1, 3, 2. So this is pretty mechanical. And since you've already know quicksort, I guess. Yeah, but any questions on 1.5?
So like once we split up all the arrays, I guess how does it come together again?
Okay, you're actually not doing a split here. It's just that so once you pick the pivot, right? In an actual array, so we're splitting it into sets so that it's like more clear how we're partitioning this. But in the actual array, it's just gonna be something like this. And once you fix the pivot, you're just gonna pick another pivot here. Say, remember how we picked 8? So this is like a pivot. It's still like the same array, really. It's just that the part that we care about that we're gonna perform quick sort. Oh, sorry. I think in the recursive case, you are actually splitting them.
Okay.
Yeah, that's a good question. Do you guys have quick sort implementation in homework or lab this week?
So I have to check. So the homework we didn't have to write quicksort, but they gave like a program that demonstrates it. So maybe like the code is there too. I just have to look.
I'll look into like the source code for quicksort and see how they piece them together.
Okay.
Yeah, because I was assuming, okay, on paper you don't have to worry about it, but when writing code,
Yeah.
yeah. Okay, so let's see, quick sort pivot choice. Yeah, Shivai, since we really ran out of time, I think what I will do is that I will continue just walking through this and just record it as part of the thing for this question too and send it to everyone. But
Okay.
feel free to leave if you want to.
Sure. Thank you.
You're welcome. So yeah, stay safe and have a great week.
Yeah, you too.
Bye.
Bye.
Hey Ryan, are you still there?
Hey.
Yeah. Oh, so yeah, I wish I have more time, but it was poor time management.
Oh, I think you did pretty well, actually. In the meeting, we talked about how we all expected to lecture for most of it. So I think you managed the time well. The worksheet was pretty long, and I think that even going through like one was like enough for students, or as expected for students. But I think you did pretty good, actually.
Thanks. It's also because like I think the week right after midterm is like the week where people are most likely to just not watch lecture and have fun.
Yeah.
At least that's the case for me. Yeah.
Mhm.
So feel free to leave, but I'm just gonna stay in this Zoom room so that I can finish recording this thing.
Okay. Oh, okay. Sounds good. I'll let you know the rest of the stuff later then.
Yeah, sure. All right,
All right.
talk to you later.
All
Bye.
right, bye.
Okay, so let's continue on this question. So we're looking at question 2, and we're in this question, we're going to explore what are some choices for quicksort such that it will give us desirable runtime, whereas what might be some pretty bad choice for the pivot such that it will actually result in a longer runtime. So this is really like a question that brings you some insight into how to choose a pivot for quicksort. And especially given that this quicksort algorithm really relies on the choice of the pivot, its runtime. Okay, so let's get started. So part A, so for each pivot selection strategy below, what is the best, average, and worst case runtime? So part A asks what will be like the best, average, and worst case runtime for always choosing the first value in the list. Well, now notice that it doesn't give you any constraint on what the list is actually like, right? So the list could be sorted, or it could just be completely random. So for this question, let's actually examine these two cases separately. So in the case that the list is sorted, then it can either be sorted in ascending order or descending order, which is going to be a reverse list, right? So in the ascending order, if you have a list, then what quicksort is going to do is that it's going to pick the first element. So in ascending order case, this is going to be the minimum value in your entire array. And then once it pick it as a pivot, it's going to group all the elements that's larger than this pivot to the right and all the elements that's smaller than this element to the left. So this means that all the 2 to the n elements are going to go to the right. And then what's it going to do is that it's for the remainder. So remember how quicksort is a recursive procedure. So then it's going to look at this remaining part and it's going to pick the smallest element yet again. So notice that each time, for each of the quicksort call, you're only reducing the size of the problem by 1, right? Because after each call, you still have, if at the current level you have k elements, then after each call, you still have k minus 1 elements unsorted. So this means that an ascending order list will give you total number of calls, will actually require n calls on quicksort. And in each call to the quicksort, because you are actually checking all the elements and then grouping them by whether it's larger or smaller than the pivot. So imagine that you are traversing through this whole thing. You're actually also doing n checks, right? So it is n calls. So what is the runtime for ascending order, an ascending order list or array? You're doing n calls, and in each of the calls, you're doing at most n checks. So this will give you a total number of n squared complexity asymptotically. Well, but notice that the ascending case is actually trivial. Why? Because if the list is already sorted, you might as well return it, right? So we don't really have to worry about the ascending case, but the reasoning we use in the ascending case will actually help us when we talk about the descending case. So the descending case is not trivial because they're in reverse order and you want them to be in ascending order. But the logic is the same in that whenever you pick the first element as your pivot, it's always going to be the largest element in your problem or in your array. So that means that it's only going to reduce the problem size by 1 because for the remainder of the thing, everything's going to be on the right of this pivot. So you'll have n minus 1 all the way to 1. And then you'll need to make another call. But in this other call, you're still picking like the first element, which is the largest. So it's essentially the same thing in that you're still doing n quicksort calls, and then in each call, you're also doing at most n word. So it's 0 n squared. So notice that in this case, this is like probably pretty time consuming as it seems, because remember procedures like merge sort, there are like n times log n, whereas this is like n squared, which is asymptotically more complex. But so now let's look at the second case. What if the list is in random order? So in the case of random order, notice that you are guaranteed that the first value of the array is actually gonna be the min or max. So that means that you have some chance, you have a pretty good chance that the pivot value that you select in this whole array is that when sorted is actually somewhere in the middle. That means you will have a very good amount of elements on the left side of the pivot and a very good amount of elements in the right side of the pivot. So that means that it will actually not give you the worst case in this case, because the chance of you always selecting like the max, the min or max element in your in the recursive part of the problem is like 1 over n, right? So if you have n elements, you only have a very little chance of encountering this case. So when we select it randomly, we'll actually have a runtime less than theta of n squared. So let's look at part B. In part B, we want to always find and choose the median value in the list. Assume finding the median takes O of n time, where n is the length of the list. So let's analyze this in terms, we can think of all the binary trees that we have, and if you draw out like the recursive diagram, it will be pretty straightforward. So notice that when you pick the median value in a list, you'll have an equal number of elements on the left and right? So if you have median here, you'll have about the same number of elements on the left side of this median and the right side of this median. So this is the same as splitting the problem into two, right? Because remember in the case of merge sort, we're just cutting the problem into two parts. Okay, so now given this subpart of the problem, we're again selecting the median. And we're again having about the equal number of elements on both the left and right. So so let's do an analysis on the runtime. So notice that if this goes on and on and on, then initially if you have a problem of n elements, it's gonna go to so this median is taken out, right? So it's gonna be n minus 1 over 2 and n minus 1 over 2. And sometimes there might these two numbers, so the number of elements in these two parts might differ by one number, because imagine like if this is an odd number, if the numerator is an odd number, then like there will be a difference of one element. But we can ignore that for asymptotic analysis, because we only care about the asymptotic order. So n minus 1 over 2 is roughly n over 2, asymptotic. And then and in this level, we're further splitting it into n over 4 and n over 4. Just like that. So now we want to see in each layer how much work is done. So let's look at this layer first. So recall how the problem says finding the median takes O of n time. So when you start from the original problem and you do your first recursive call, it takes O of n time to find the median. So it takes the amount of time taken for this call, for this layer, depends on their parent. So this is O of n. So you'll have a total amount of n work done in this layer. And in the second layer, you're splitting an n over 2 size array into two n over 4 subparts, and it takes O of n over 2 time to find the median. And since finding the median is like the only thing you're doing at each layer, so that constitutes like all the work you've done. This is n over 2 and n over 2, and these two n over 2 they sum up to n work. So recursively, you'll realize that at each layer you're always doing n work, and you have log n layers. You have log n layers again. So this will give you a total number of O of n log n, including the time that you find the median. Yeah. So once we draw out this, let me remove these red things. So a good approach to think about these is always to draw out like a recursion diagram where you can see like how the problems are increasing at each layer, and you can compute, and then you compute the work done at each layer and just sum up them using like the number of layers you have. And now you also want to choose like, so now you want to analyze the case where you always choose a random pivot. So notice that this is essentially the same as choosing the first value in the list, where a list is in random order. So in this case, notice that it is possible that when we do a random selection, we actually pick like the min or max value of the array, which will bring us back into this horrible case where we have n squared. But and previously I've proven that the chance of this happening is actually quite low. But let's do a mathematical analysis of how unlikely this is gonna happen. So if we start from an array of n, and we're gonna pick the pivot, the chance of us picking the min or max value of this array will be 1 over n, right? But for this worst case to happen, we need to make sure that once we pick this median, so once we have this array split, for each of the sub-arrays, we also have to pick like, you know, the worst case, which is like the min or max value in this case. And notice that we have in total n over 1 elements to pick from, and there's only one min or max value from this n minus 1 elements, right? So what in the second call, the chance that we actually pick a horrible pivot that is like the min or max value of the entire remaining problem is 1 over n minus 1, where n minus 1 is the total number of choices. So if we think about this problem recursively, then in the third call, we'll have a chance of 1 over n minus 2 to pick the min or max value as the pivot. So if you have taken any probability class, then this entire thing is just 1 over n factorial. And this is a very small number. So the chance of us, if we always choose a random pivot, the chance of us getting the worst runtime possible is about 1 over n factorial, which is like a very, very small number. So most of the time when we choose a random pivot, our runtime is going to be in between n log n, which is the best case. Remember, always picking the median, and O of n squared. So it's going to be in between these two runtime. Okay, so that is the entire idea of this problem. And I'll stop there, and just want to thank you guys for, if you are watching this video, then thanks for watching, and I'll see you next time.